Consider a simple experiment. You take a coin and flip it, heads or tails. You flip it again, then again. The outcome each time feels random, unpredictable, almost trivial. But if you were asked to map out every possible sequence of results from 266 coin flips, you would be looking at a number larger than the count of every atom in the observable universe. Not just larger, incomprehensibly, cosmically, absurdly larger. And here is the strange part. That staggering complexity does not come from anything exotic. It comes from nothing more than a simple coin. The universe is at its foundation, a place of extraordinary complexity dressed up in a skin of apparent simplicity. And every now and then, a discovery comes along that tears the skin back and forces us to look directly at what is underneath. Quantum computing is one of those discoveries, but it is not a discovery in the way most technology is described. It is not simply a faster version of what came before. It is not a bigger engine in the same car. It is a fundamentally different way of processing information, one that draws directly from the strange and counterintuitive rules that govern the universe at its smallest scales. To understand why quantum computing matters, you first need to understand what classical computing cannot do. And once you see that gap, once you really grasp the shape of what lies on the other side of it, the entire story changes. Classical computers, the machines that power every smartphone, every data center, every streaming service, every financial transaction in the modern world, work by processing information as bits. A bit is the smallest possible unit of information. It is either a 0 or a 1, on or off. Every calculation a classical computer performs, no matter how complex, is built from these two states. The entire computational history of modern civilization, every spreadsheet, every photograph, every video call, every weather forecast, every genome sequencing project, is ultimately the result of billions of tiny switches flipping between 0 and 1 in precisely choreographed sequences. That this is not a criticism. It is an astonishing engineering achievement. Classical computers have transformed human civilization at a pace nothing in history comes close to matching. In roughly 70 years, we went from machines that filled entire rooms and calculated artillery trajectories to pocket-sized devices that can render for environments in real time while simultaneously streaming music and translating speech between languages. The progress has been staggering, but it has always been progress within a fixed set of rules, and those rules have limits. Hard, mathematical, unavoidable limits. The problem is this: some problems do not simply get harder as they grow. They get harder exponentially. Doubling the size of the problem does not double the difficulty. It multiplies the difficulty by a factor that can overwhelm even the most powerful computing infrastructure ever built. Simulating how the electrons in a molecule interact is one such problem. A molecule with just a few dozen atoms requires tracking an exponentially growing number of quantum interactions between its electrons. Even for a relatively modest molecule, the number of variables quickly exceeds anything a classical computer can manage. Not because the computers are slow, but because the problem fundamentally requires representing a space of possibilities that classical bits cannot efficiently encode. Cracking certain types of encryption, optimizing genuinely complex logistical systems with thousands of interdependent variables, finding the folded structure of a novel protein. These are all problems that sit in a territory where classical computing approaches its wall, and it has been sitting at that wall for a long time. In 1980, a physicist named Paul Benioff proposed something that seemed, at the time, closer to a thought experiment than a practical engineering proposal. He described a computer that did not process information using ordinary binary bits, but using quantum mechanical systems, units that followed the deeply strange rules of quantum physics. Benioff was building on theoretical groundwork laid by researchers, exploring the fundamental connection between physics and computation. His quantum Turing machine, as it became known, was the first formal model of a computer that operated according to quantum mechanical principles. The timing was not accidental. Physicists were already running into the same wall. When researchers tried to use classical computers to simulate quantum systems, the computational cost exploded out of control with even modest system sizes. The quantum world simply had too many possible configurations for classical bits to track. The physicist Richard Feynman made this point with characteristic directness. If you want to simulate nature, and nature is quantum mechanical, then you need a quantum mechanical simulator. A classical computer trying to simulate a quantum system is like trying to describe a three-dimensional sculpture using only a flat photograph. You can capture something, but you inevitably lose information, and the loss compounds as the system grows. The physicist Yuri Manin had arrived at a similar conclusion independently. Both Feynman and Manin recognized that the exponential complexity of quantum systems was not a bug to be engineered around. It was a feature of reality, and to harness it rather than fight it, you needed a machine built from the same fabric. That insight, sitting at the intersection of fundamental physics and theoretical computer science, took decades to move from paper to hardware. But while the engineering challenges remained formidable, the theoretical framework was already producing remarkable applications. One of the earliest and most consequential came not from computation, but from communication. In 1984, Charles Bennett and Gilla Brassard published a proposal for a communication protocol unlike anything that had come before. It was called quantum key distribution, and it used the behavior of individual photons to create an encryption system that was not merely computationally difficult to break. It was physically impossible to break without leaving a detectable trace. The distinction is profound. Every classical encryption system in use today depends on mathematical difficulty. The assumption is that an adversary, even a very powerful one, would need an impractical amount of computing time to crack the code. But that assumption rests on the limits of available technology. If the technology changes, the security changes. Quantum key distribution rests on something more fundamental: the laws of physics themselves. The protocol works like this. Imagine two people, call them Albert and Catherine, who want to establish a shared secret key that they can later use to encrypt their communications. Albert sends Catherine a stream of photons, each encoding a bit of information through its quantum state, specifically through the orientation of its polarization. The key is that quantum states cannot be observed without being disturbed. If a third party, call her Ella, attempts to intercept the photons and measure them to learn the key, the very act of measurement changes the quantum states of those photons. When Albert and Catherine later compare a sample of their results over a public channel, they will see statistical anomalies that reveal Ella's presence. No interception can be hidden. No eavesdropping can be perfectly concealed. The protocol does not make it harder to spy. It makes it physically impossible to spy undetected. This was not a theoretical curiosity. Quantum key distribution has moved steadily toward real-world deployment. It is being tested in satellite-based communication networks. It is being used in financial institutions where the security of transmitted information is a matter of enormous consequence. China launched a satellite in 2016 specifically designed to test quantum encrypted communications over intercontinental distances, and in subsequent years demonstrated quantum key distribution between ground stations separated by over 1,000 kilometers. The physics of the early 1980s has become infrastructure, But quantum key distribution was really just the opening act of a much larger story. While it used quantum mechanics to protect information, the deeper question was whether quantum mechanics could be used to process information in ways that classical systems fundamentally could not. The answer turns out to be yes, and the mechanism behind that answer is one of the strangest features of the quantum world. In classical computing, a bit is always either 0 or 1. At any given moment, it occupies exactly one of those two states. A quantum bit, or qubit, can exist in what is called a superposition of 0 and 1 simultaneously. This is not a claim that the qubit is both 0 and 1 exactly, in the way you might think of a coin that has not yet landed. It is a precise mathematical statement about the qubit's quantum state. Before measurement, the qubit does not have a definite value. It exists in a combination of possibilities, each with an associated probability amplitude. When you measure the qubit, it collapses to a definite value, 0 or 1, with probabilities determined by that quantum state. The power of superposition becomes apparent when you scale up. A single classical bit holds one value. Two classical bits can together represent one of 4 possible combinations, but only one at a time. 3 bits can represent one of 8 possible combinations, again only one at a time. With 2 qubits in superposition, you can simultaneously represent all 4 possible 2-bit combinations. With 3 qubits, all 8. With 10 qubits, all 1024. With 300 qubits, the number of states you can simultaneously represent exceeds the number of particles in the observable universe, not by a small margin, by an amount that makes the comparison meaningless. This is not magic, and it does not automatically make every problem easy. Superposition is a resource, but it is a resource that must be harnessed carefully with precisely designed algorithms. Simply putting qubits into superposition and measuring them would give you random results. The art of quantum computing lies in using quantum operations to manipulate those superpositions so that the probability amplitudes of correct answers are amplified and those of incorrect answers are suppressed. When you then measure, you get the right answer with high probability. Alongside superposition, quantum computers exploit a second phenomenon called entanglement. When 2 or more qubits become entangled, their quantum states become correlated in a way that has no classical analog. Measuring one entangled qubit instantly determines information about the state of the other, regardless of the physical distance between them. Einstein famously found this troubling, describing it as spooky action at a distance, because it seemed to suggest some form of instantaneous influence stretching across space. Decades of experiments, culminating in the Nobel Prize-winning work recognized in 2022, have confirmed that entanglement is real and that the correlations it produces cannot be explained by any hidden classical variables. The universe genuinely does behave this way. In quantum computing, entanglement allows qubits to coordinate their states in ways that create computational dependencies no classical system can efficiently replicate. It is the feature that makes certain quantum algorithms dramatically more powerful than any classical counterpart. Not just faster in the sense of doing the same operations more quickly, but capable of following completely different computational paths. The third major resource quantum computers leverage is interference. Quantum states, like waves, can interfere with one another. Paths through a quantum computation that lead to wrong answers can be made to destructively interfere, cancelling each other out. Paths that lead to correct answers constructively interfere, amplifying the probability of those outcomes. Designing a quantum algorithm means engineering this interference precisely, so that when you finally measure the system, the answer you want emerges with overwhelming probability. Together, superposition, entanglement, and interference constitute a completely different computational toolkit than the one classical computers use. They do not simply allow quantum computers to do classical computations faster. They allow quantum computers to follow paths through information space that are simply not accessible to classical machines. The most famous demonstration of this is an algorithm developed in 1994 by a mathematician named Peter Shor. Shor's algorithm solves a specific problem: the factorization of large numbers into their prime constituents, with an efficiency that is exponentially better than any known classical algorithm. This matters because the security of the most widely used encryption on the internet, the RSA protocol that protects online banking, private communications, government networks, and an enormous fraction of all digital infrastructure, rests entirely on the assumption that factoring large numbers is computationally intractable. The RSA system works by exploiting asymmetry. Multiplying two large prime numbers together is easy. A computer can do it in fractions of a second. But running the process in reverse, starting with the product and finding the original two primes, is extraordinarily hard. When RSA was designed, the assumption was that no efficient algorithm for this reverse problem existed or would exist. For classical computers, that assumption has held. The largest number successfully factored using classical methods required computational effort equivalent to roughly 2,000 years of continuous computation distributed across many machines. In practical terms, RSA encryption is safe against any classical adversary. Shor's algorithm changes the picture entirely. A sufficiently large and error-corrected quantum computer running Shor's algorithm could factor a 2048-bit RSA number in a matter of hours rather than millions of years. The mathematical scaffolding that underlies internet security would not just crack, it would dissolve. This is why the development of quantum computing has triggered a global race in cryptography research. Governments, financial institutions, and technology companies are actively working on what is called post-quantum cryptography, designing encryption systems whose security does not depend on the difficulty of factoring, and which would therefore remain secure even in a world with powerful quantum computers. The United States National Institute of Standards and Technology announced its selection of the first post-quantum cryptographic standards. The timeline for quantum computing to break current encryption is uncertain, but the preparation has already begun. Beyond cryptography, Shor's algorithm is a demonstration of principle. It shows that quantum computers can solve at least some problems in fundamentally different complexity classes than classical machines. The question of exactly which problems quantum computers can efficiently solve, and which they cannot, is one of the most active areas of research in theoretical computer science. Another landmark is Grover's algorithm, developed in 1996 by Loaf Grover. While Shor's algorithm provides an exponential speedup for factoring, Grover's provides a quadratic speedup for searching an unsorted database. If a classical computer searching a list of 1 million items would require on average 500,000 checks, Grover's algorithm would require roughly 1,000. This sounds less dramatic than Shor's result, but for many practical problems involving search and optimization, even a quadratic speedup represents an enormous advantage. It also reveals something interesting about the nature of quantum computational advantage. It is not a uniform property. Some problems receive exponential benefits from quantum computing. Others receive more modest, but still significant benefits. And many problems, perhaps the majority of everyday computational tasks, receive no meaningful benefit at all. This is worth sitting with for a moment. Quantum computers are not a universal accelerant for all computation. The common perception that quantum computers will simply do everything faster is wrong. streaming a video, running a word processor, rendering a web page, executing most machine learning inference tasks. These are jobs for classical computers, and they will likely remain so. The structure of these problems does not align with the mechanisms that make quantum computing powerful. Using a quantum computer for email would be approximately as sensible as using a particle accelerator to boil water. Technically, you could arrange for it to happen, but the tool is not matched to the task. What quantum computers do exceptionally well is a specific and important subset of problems, where the solution can be found by constructive interference of correct paths through an enormous space of possibilities. Simulation of quantum mechanical systems is the most natural application, because quantum computers literally speak the same mathematical language as the systems they are simulating. Drug discovery stands to be transformed, because the key bottleneck in designing new pharmaceuticals is understanding how molecules interact at the quantum level. A quantum computer could, in principle, simulate the full quantum mechanical behavior of a drug candidate's interactions with a target protein, something that is simply not computationally feasible with classical hardware for molecules of biologically relevant complexity. Materials. Science offers similarly compelling possibilities. The properties of materials, from superconductivity to catalytic efficiency to the efficiency of solar cells, emerge from quantum mechanical behavior at the electronic level. Designing new materials with specific properties is currently constrained by our inability to simulate those quantum behaviors efficiently. Quantum computers could remove that constraint, opening the door to materials that do not yet exist and properties that we currently cannot engineer toward. Climate modeling, financial optimization, logistics, machine learning training. These are areas where quantum advantage may emerge in more targeted ways, not necessarily by replacing classical approaches wholesale, but by solving specific sub-problems that currently represent bottlenecks. The path from theoretical quantum advantage to practical quantum utility, however, runs through a formidable set of engineering challenges that are worth understanding in detail, because the gap between what quantum computers can do in principle and what they can do today is very large. The central challenge is qubits must maintain their quantum states, their superpositions and entanglements throughout a computation, but quantum states are extraordinarily sensitive to their environment. Any interaction with the surrounding world, a stray photon, a tiny fluctuation in magnetic field, a vibration, thermal noise from the equipment itself, can cause the quantum state to collapse prematurely. When that happens, the computation fails. This vulnerability to environmental disturbance is called decoherence, and managing it is the defining engineering challenge of quantum computing. Current quantum computers address this partially by operating at temperatures close to absolute zero, near -273 degrees Celsius, colder than interstellar space. At these temperatures, thermal noise is suppressed enough to allow qubits to maintain their coherence for the brief windows of time required for a computation. But even with this extreme cooling, decoherence is a constant threat. The practical consequence is errors. Quantum computations are noisy. Qubits make mistakes. Gates, the quantum operations applied to qubits, are not perfectly executed. After a certain number of operations, the accumulated error degrades the computation to the point where the output is unreliable. This imposes a hard limit on the depth, meaning the number of sequential operations of any computation that can be run on current quantum hardware. Quantum error correction is the field dedicated to solving this problem. The basic idea is to encode one logical qubit, the qubit that does useful computation, across many physical qubits, so that errors in any individual physical qubit can be detected and corrected without disturbing the logical qubit's state. The surface code, the most actively developed error correction scheme, can protect a logical qubit against errors provided that individual physical qubit error rates are below a threshold of roughly 1% per operation. Below that threshold, adding more physical qubits improves the reliability of the logical qubit exponentially. Above it, the errors accumulate faster than correction can keep up. Current state-of-the-art physical qubit error rates are approaching that threshold, but have not uniformly crossed it, and the ratio of physical qubits to logical qubits required for useful fault-tolerant computation is daunting. To run Shor's algorithm against a real-world 2048-bit RSA key would require, by current estimates, somewhere between several million to tens of millions of physical qubits arranged in a fault-tolerant architecture. The most advanced quantum processors in existence today operate with on the order of tens to hundreds of physical qubits. This is not a reason for pessimism. It is context for understanding where we are in the development trajectory of a technology that is, by any reasonable measure, still in its infancy. Classical computers took decades to move from room-filling machines that performed basic arithmetic to the devices we carry in our pockets. The arc of quantum computing development is not perfectly analogous, but the principle that early stages look nothing like mature stages applies. In late 2024, Google announced its Willow quantum processor. Willow is a 105-qubit chip that represents a significant step in error correction performance. Critically, Willow demonstrated that, as the number of qubits in its error correction structure was scaled up, the error rate decreased rather than increased. This is a threshold that quantum computing researchers have been working toward for years, because it means that more qubits translates to better performance rather than more noise. It validates the fundamental approach of fault-tolerant quantum computing and represents a qualitative shift in experimental capability. Google also reported that Willow performed a specific benchmark computation in under 5 minutes that would take the fastest classical supercomputers in existence an amount of time that is longer than the current age of the universe. This headline figure deserves some careful interpretation. The computation in question was specifically chosen to be something quantum computers are good at and classical computers are not. It was not solving a problem with immediate real-world applications. It was a demonstration of quantum advantage on a carefully selected task, a proof that the capability gap is real and measurable. What it demonstrated was that quantum processors can now genuinely outperform classical computers on at least some tasks, and that this advantage is not marginal but fundamental. Similarly, IBM has pursued a parallel track of quantum processor development, with their own roadmap targeting increasingly capable hardware. The company Intel, the startup Regity, IonQ using trapped ion qubits, Quantinuum, and others are exploring different physical implementations of quantum computing, from superconducting circuits to photonics to neutral atoms. Each approach has different trade-off profiles for coherence time, gate fidelity, connectivity, and scalability. The field is genuinely experimental in the original sense, trying many different paths to see which ones lead somewhere. One of the more unexpected intersections in recent years has been between quantum computing and artificial intelligence. AI, powered by classical hardware, has demonstrated capabilities that have surprised even its creators. The protein folding problem that stumped structural biologists for decades was solved by DeepMind's AlphaFold system using deep learning on classical hardware. Systems like large language models, generative image systems, and reinforcement learning agents have demonstrated competencies in domains that were once assumed to require deeper forms of intelligence than any current machine possesses. Some researchers have suggested that as AI training methods improve and training datasets grow, AI might encroach on territory once thought reserved for quantum computing. For some problems, very large classical AI systems trained on the right data might produce accurate approximations to results that would formally require quantum simulation. This is an active area of research, and the boundaries are genuinely unclear. But AI and quantum computing are not in competition. They are, more precisely, tools suited to different aspects of the same underlying challenge: how to extract understanding from an extraordinarily complex universe. AI is exceptionally powerful for pattern recognition, generalization from data, and navigating problems with vast solution spaces where the structure of the problem can be learned rather than specified. Quantum computing is powerful for problems where the structure of the problem is inherently quantum mechanical, or where the exponential complexity of classical simulation can be shortcut by quantum mechanical operations. It is entirely plausible that the most powerful computational systems of the future will be hybrid architectures, classical processors handling the parts of a computation that they do well, quantum processors handling the quantum mechanical bottlenecks, and AI systems trained to optimize the handoffs between them. The question of which tool solves which part of which problem will itself be a rich research area for decades. One of the most philosophically resonant developments in quantum computing research came in late 2022 when a team of physicists used Google's Sycamore quantum processor to simulate behavior that mirrored the properties of a theoretical wormhole. The result made international headlines, though the interpretation required considerable care. A wormhole, in the language of general relativity, is a hypothetical tunnel through space-time connecting to distant regions. The simplest version of such a structure was described theoretically by Albert Einstein and Nathan Rosen in 1935, and is sometimes called an Einstein-Rosen bridge. Whether physical wormholes actually exist in the universe is unknown. None has ever been observed, but they are consistent solutions to Einstein's equations of general relativity, and they appear in a number of theoretical contexts as useful conceptual tools. What the Sycamore experiment did was to implement a quantum simulation based on a theoretical framework called the holographic principle, specifically a version of a deep conjecture in theoretical physics called gauge gravity duality. This conjecture, developed by Juan Maldacena in 1997, proposes a mathematical correspondence between a theory of quantum gravity in a curved spacetime and a quantum field theory without gravity living on the lower dimensional boundary of that spacetime. The two descriptions are mathematically equivalent, even though one includes gravity and the other does not. In this correspondence, phenomena that look like a wormhole in the gravitational description can correspond to quantum entanglement in the boundary description. The Sycamore experiment implemented a small, highly simplified quantum system designed to exhibit dynamics that, in this theoretical framework, correspond to information transmission through a wormhole-like structure. The researchers encoded quantum information into one side of the system, transmitted it through the circuit, and observed it emerge at the other side in a manner consistent with what the holographic framework predicts for wormhole traversal. The experiment was not creating a physical wormhole. Nothing was warping space-time in Google's quantum computing laboratory, but it was, in a precise technical sense, simulating dynamics that are mathematically equivalent to wormhole traversal within a specific theoretical model of quantum gravity. The reason this matters is not the wormhole itself, but what the experiment represents. The deepest unsolved problem in fundamental physics is the reconciliation of quantum mechanics and general relativity. Quantum mechanics describes the world of the very small with extraordinary precision. General relativity describes gravity and the large-scale structure of space-time with equal precision. But the two frameworks are mathematically incompatible. They rest on different foundations and cannot both be literally true in their current forms at the extreme conditions where both become important. For instance, at the center of a black hole or at the moment of the Big Bang. Reconciling them is the work of quantum gravity, and it has resisted solution for nearly a century. What experiments like the Sycamore wormhole simulation offer is an empirical window into the kind of physics that quantum gravity theorists spend their careers analyzing only on paper. A quantum computer, because it operates according to quantum mechanical principles, can simulate quantum gravitational scenarios in ways that classical computers cannot. As quantum hardware becomes more powerful, these simulations will become more realistic and more detailed. This suggests a future in which quantum computers serve not just as computational tools, but as scientific instruments, devices for probing regions of physics that no experiment in a conventional laboratory could access. Black hole dynamics, the behavior of space-time at the Planck scale, the early universe conditions during which the universe underwent rapid expansion. These are domains where quantum computation may provide our only empirical foothold short of technology we cannot currently imagine. The physicist Seth Lloyd has described the universe itself as a quantum computer. The idea is that every physical interaction between particles constitutes an elementary computation, a transformation of quantum information that proceeds according to the laws of quantum mechanics. In this view, the universe is not merely described by mathematics. It computes its own evolution, processing information at a density and scale that dwarfs anything we have built or could build. Every collision between atoms, every photon absorbed or emitted, every entanglement formed and broken is a step in an ongoing computation of cosmic scale. This perspective connects quantum computing to a set of deep questions about the nature of physical law. Why should the universe be computable at all? Why should the laws of physics take a form that admits of mathematical description? Is computation a fundamental feature of reality, or is it a lens we impose on a reality that is something more or less than information? These questions do not yet have definitive answers. They sit at the intersection of physics, mathematics, philosophy of science, and the emerging science of information. But quantum computing makes them sharper and more concrete than they have ever been. Consider what it means that a quantum processor can simulate the dynamics of a theoretical wormhole. If the universe is running a computation, quantum computers are, in some sense, emulators, machines that can replicate, within a controlled context, aspects of the universe's own processing. Every time a quantum circuit correctly models a quantum system, it is doing something that no other physical device can do. It is thinking the same way nature thinks, solving problems by the same methods nature uses, not approximating quantum behavior with classical proxies, but actually being quantum mechanical. This is the deepest reason quantum computing represents a conceptual breakthrough, separate from any specific application. It is the first technology humans have built that operates according to the same computational principles as the universe at its most fundamental level. Classical computers are extraordinary machines that have transformed civilization, but they are, ultimately, fast manipulators of simple binary states. They model the world from the outside. Quantum computers step inside, now step back for a moment and return to the coin. 266 flips. A space of possibilities larger than the universe's atom count. The reason this example is useful is not because it describes an interesting party trick. It is because it illuminates something important about the relationship between complexity and comprehension. Humans are pattern finders. We evolved in an environment where the patterns that mattered were relatively simple, where food was, where danger was, where shelter was. Our cognitive architecture is optimized for navigating this kind of structured simplicity, the deeper structure of the universe. The quantum mechanical layer, where particles exist in superpositions and entangled states correlate instantaneously across space, is not accessible to direct intuition. We cannot see it, feel it, or experience it at the scale of ordinary life, but we can represent it mathematically. And once we have a mathematical representation, we can ask whether there is a physical system that naturally implements that mathematics. The answer for quantum mechanics is yes. Qubits are physical systems whose natural dynamics implement the mathematics of quantum mechanics. This is the foundational insight that makes quantum computing possible and makes it qualitatively different from anything that preceded it. Our bias toward simplicity runs very deep. We build models that explain phenomena in the simplest terms our cognitive frameworks can handle. Not because the universe is simple, but because simplicity is what we can process. The history of science is, in part, a history of discovering that the universe is more complex than our models assume, and then building new tools, mathematical and physical, that can handle more of that complexity. Classical computers were a tool for handling combinatorial complexity that exceeded human mental arithmetic. They were genuinely revolutionary, but they are still, fundamentally, tools for solving problems framed in the language of classical logic. Every problem a classical computer solves is broken down into binary operations. Every byte of data is a string of zeros and ones. The entire computational architecture assumes a world that is, at some level, binary. The universe is not binary. It is quantum mechanical. And quantum computers are the first tools we have built that take that seriously. There is something humbling and exhilarating in equal measure about where this leads. Quantum computing is not yet mature. The gap between the theoretical promise and the current engineering reality is wide. Fault-tolerant quantum computers with millions of well-corrected logical qubits do not exist today. The timeline for when they will exist is genuinely uncertain. Researchers who follow the field closely give estimates ranging from a decade to several decades for quantum computers that can definitively break RSA encryption or reliably simulate large, biologically relevant molecules. But the trajectory is real. Error rates are declining. Qubit counts are increasing. Error correction techniques are improving. New physical implementations are demonstrating coherence times and gate fidelities that would have seemed implausible a decade ago. The field is not stagnating. It is moving, and the milestones that have been passed, from the first experimental demonstration of quantum advantage to the Willow processor's error correction scaling, represent genuine engineering progress. The scientific and social implications are already being taken seriously. The cryptographic transition is underway. Governments and standards bodies are not waiting for a large-scale quantum computer to actually break encryption before establishing post-quantum standards. They are acting now because the preparation time for a cryptographic transition, the time required to update every piece of software and hardware that depends on current encryption standards, is measured in decades. The transition must begin long before the threat materializes. This is not panic. It is prudent systems thinking. The same kind of prudent thinking that led Bennett and Brassard in 1984 to recognize that quantum mechanics could be used to secure communication, decades before the hardware existed to threaten it. What remains unknown is at least as interesting as what has been learned. We do not yet know which physical implementation of qubits will prove most scalable. Superconducting qubits currently lead in qubit count, but trapped ion systems demonstrate higher gate fidelities. Photonic approaches offer room temperature operation, but face different challenges in creating the entanglement needed for computation. Neutral atoms arranged in optical arrays show promise for certain architectures. There is no clear winner yet, and it is entirely possible that the dominant architecture of mature quantum computing is one not yet fully explored. We do not know how quantum computing and artificial intelligence will interact in the long run, whether quantum hardware will provide training speedups for future AI systems, whether AI-designed quantum circuits will outperform human-designed ones, whether the combination of the two will open problem domains neither can reach independently. These are live research questions. We do not know whether there exist quantum algorithms for problems currently thought to require classical approaches, or whether there are classical algorithms that can simulate quantum systems more efficiently than is currently believed. The theoretical landscape of quantum computational complexity is still being mapped. There are fundamental questions about quantum speedup, about the relationship between quantum and classical complexity classes, that remain open, and we do not know, at the deepest level, what the universe's own information processing nature tells us about reality. If quantum computers are emulators of the universe's own computations, what does that mean for the distinction between simulation and reality? If information is a fundamental physical quantity, as many physicists now believe, then understanding how information is processed at the quantum level may turn out to be understanding something central about what the universe is. These questions are not idle speculation. They are the direction in which serious physics is moving. The experiment on the Sycamore processor that simulated wormhole dynamics was not a sideshow. It was a demonstration of a research program using quantum hardware to probe quantum gravity that may represent one of the most important scientific frontiers of the coming decades. What started as a physicist's thought experiment in 1980 has become a global technology race, a fundamental shift in cryptographic strategy, a new tool for materials and pharmaceutical research, and a scientific instrument for probing the deepest questions about the nature of space-time and information. The coin flip that seemed trivial has opened into a vista of complexity that classical tools cannot traverse. Quantum computers will not solve every problem. They will not replace the devices you use every day. They will not make most of the digital infrastructure of modern life faster or cheaper. But for the specific problems that stand at the limit of what human civilization can compute, the places where our questions outrun our tools, quantum computing is the most powerful direction anyone has found. It is not magic, it is physics, and the physics has only just begun to be translated into engineering at scale. If you found yourself thinking differently about computation, about complexity, or about what it means to build a machine that thinks the way the universe thinks, take a moment to share this video with someone who would appreciate it. The ideas here are genuinely worth discussing. There is a lot more to come from this field, and the story is far from over. To fully appreciate what is being built here, it helps to go back further than 1980, back to the intellectual foundations of both computing and quantum mechanics, and to understand how long the threads leading to quantum computers have actually been running. The theory of computation itself is barely a century old as a formal discipline. In 1936, Alan Turing published his foundational paper describing the abstract logical machine that now bears his name. A Turing machine is an idealized device that reads and writes symbols on an infinite tape according to a set of rules, and it can, in principle, simulate any computation that any physical device can perform. The concept was not about hardware. It was about the abstract structure of what it means to compute something, to follow a procedure, to execute an algorithm. Turing's insight was enormously productive. It gave computer scientists a formal language for asking what can and cannot be computed, what is solvable in principle and what is not, and how computational difficulty scales with problem size. The entire edifice of theoretical computer science rests on foundations Turing laid. But Turing's machine was a classical machine. It processed symbols one at a time. It was, in the language of physics, entirely deterministic and entirely classical. Quantum mechanics had been developing in parallel over the same period. Beginning with Max Planck's proposal in 1900 that energy was exchanged in discrete quanta, continuing through Einstein's explanation of the photoelectric effect in through Niels Bohr's model of the hydrogen atom, and crystallizing in the mid-1920s with the formulation of quantum mechanics proper by Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others. By 1930, quantum mechanics was essentially complete as a mathematical framework. Its predictions agreed with experiment to extraordinary precision, but its interpretation remained, and in many ways still remains, deeply contested. The Schrödinger equation is the mathematical engine at the heart of quantum mechanics. It describes how the quantum state of a system evolves over time, and the state it describes is not a list of definite values. It is a wave function, a mathematical object that assigns a probability amplitude to every possible configuration of the system. The square of the amplitude gives the probability of finding the system in that configuration upon measurement. Before measurement, the system is in a superposition of all those configurations simultaneously. After measurement, it collapses to a single definite configuration, with the probabilities given by the wave function. This is not an approximate description. It is the literal content of the theory. Quantum mechanics does not say that. Particles have definite positions and velocities that we merely fail to observe with sufficient precision. It says that prior to measurement, definite positions and velocities do not exist in the way classical physics assumed they did. The universe at its smallest scales is genuinely probabilistic, genuinely superposed, genuinely entangled. This is not a matter of incomplete knowledge. It is a feature of the physical world. Einstein spent much of the latter part of his life uncomfortable with this conclusion. His famous objection that God does not play dice with the universe was not, as it is sometimes caricatured, a general aversion to probability. Einstein was perfectly comfortable with probabilistic theories. His discomfort was with the idea that the quantum mechanical probabilities were fundamental, that there was nothing underneath them, no hidden reality of definite values waiting to be uncovered. The experiments of the subsequent decades, and particularly the results from John Bell's inequality tests and their experimental implementations by Alan Aspect in the 1980s and later by many others, settled the question definitively in quantum mechanics' favor. The world is not locally realistic in the sense Einstein preferred. Quantum entanglement is real. The universe does not have hidden variables that predetermine measurement outcomes in the way classical physics would require. This background matters for understanding quantum computing, because quantum computing is not simply using physics to do computation faster. It is using the actual structure of quantum mechanics, the superpositions, the entanglements, the interference patterns, as the computational resource. When a quantum computer runs an algorithm, the quantum state of its qubits passes through a sequence of transformations. These transformations are unitary operations, the quantum mechanical generalization of rotations. They are reversible. They preserve the total probability in the quantum state, and they operate on the entire superposition simultaneously. The mathematical structure of quantum computation is therefore genuinely different from classical computation, not just in efficiency but in kind. A classical computation proceeds through a sequence of definite states. At every moment, the bits of the computer have definite values, 0 or 1. A quantum computation proceeds through a sequence of superposed states. At every moment, the qubits of the computer exist in a superposition of exponentially many different configurations. The history of the computation does not trace a single path through state space. It traces all paths simultaneously, with each path accumulating a phase, a complex number, that can constructively or destructively interfere with other paths. This is what makes Shor's algorithm work. When the algorithm runs, it sets up a quantum state that represents a superposition of all possible guesses for the factors of a large number. It then applies a series of operations that cause the phase relationships between these possibilities to evolve in a specific way. When the right factors contribute to the answer, the paths leading to them constructively interfere, making them more probable. When wrong factors contribute, their paths destructively interfere, making them less probable. When you finally measure, the right answer comes out with high probability. The algorithm has exploited the physics of quantum mechanics to explore an exponentially large space of possibilities in a way that a classical computation, which must evaluate each possibility separately, simply cannot. Understanding this also helps clarify what quantum computers cannot do. For a problem to benefit from quantum computational methods, it needs to have a structure that quantum interference can exploit. The problem needs to admit a quantum algorithm that can amplify correct answers and suppress incorrect ones. For a large fraction of problems, no such algorithm is known or may even exist. The question of which problems admit efficient quantum algorithms is one of the deepest open questions in theoretical computer science. The complexity class of problems efficiently solvable by a quantum computer is called BQP, which stands for Bounded Dara Quantum Polynomial Time. The class of problems efficiently solvable by a classical computer is called P for polynomial time, and its probabilistic extension is called BPP. Shor's algorithm shows that the integer factorization problem, which is believed to be outside BPP, is inside BQP. The relationship between BQP and other classical complexity classes is not fully understood. It is not even known for certain whether quantum computers can solve all NP problems efficiently. That is, whether BQP contains NP. Most researchers believe it does not, meaning that quantum computers are not general-purpose solvers for all hard problems. They provide a specific kind of advantage for a specific kind of problem structure. NP problems are problems where, given a potential solution, you can quickly verify whether it is correct, even though finding the solution in the first place might be very hard. The traveling salesman problem is an example. Finding the shortest route through a set of cities grows exponentially harder as the number of cities increases. But if someone hands you a route, you can quickly check whether it is shorter than any other route you have seen. Many of the most important practical optimization problems are NP problems, and it was a significant result that quantum computers do not appear to make all of them easy. This points to a nuanced but important truth about quantum computing. The field is not about making everything faster. It is about identifying specific problem structures where quantum mechanical resources, superposition, entanglement, and interference can be strategically deployed to achieve what no classical approach can match. This requires algorithm design, hardware engineering, and a deep understanding of both the mathematical structure of problems and the physical structure of quantum systems. It is not one discipline, but several, converged on a common aim. The experimental progress in quantum hardware over the past decade has been driven by several parallel communities working on different physical platforms, and comparing them reveals how much uncertainty remains about which approach will ultimately prove most scalable. Superconducting qubits. The technology underlying the processors built by Google, IBM, and others work by cooling metal circuits to temperatures near absolute zero until they exhibit superconductivity, meaning they conduct electricity with zero resistance. In this state, the circuits can be engineered to behave as quantum two-level systems, qubits. Superconducting qubits can be manufactured using techniques derived from standard chip fabrication, which is a significant practical advantage because it means the field can leverage an enormous existing industrial infrastructure. They can be operated with fast gates, meaning quantum operations are executed quickly, which is important because coherence times are finite and faster gates allow more operations before decoherence sets in. The drawback is that coherence times are still relatively short, on the order of microseconds, 2 milliseconds in the best current devices, and the extreme cooling required means the hardware is bulky and expensive. Trapped ion qubits work on a completely different principle. Individual ions, electrically charged atoms, are suspended in electromagnetic traps and cooled using lasers to nearly absolute zero. Their internal electronic energy levels serve as the qubit states. Trapped ions have longer coherence times than superconducting qubits, sometimes by orders of magnitude, and they can achieve higher gate fidelities. The drawback is that gate operations are slower, and scaling to large numbers of qubits while maintaining high connectivity is technically challenging. Companies like IonQ and Quantinium have been developing trapped ion quantum computers, and this platform has demonstrated some of the highest quality qubit operations achieved to date. Photonic quantum computing uses individual photons as qubits, encoded in properties like polarization or path. Photons interact weakly with their environment, giving them excellent coherence properties. They can travel long distances without decohering, which makes photonic approaches particularly attractive for quantum communication networks. The challenge is that photons do not interact with each other easily, which makes Qubit gate operations, the operations that create entanglement, technically difficult. Recent progress in integrated photonic circuits and specialized optical devices has advanced the field, but photonic quantum computing remains less mature than superconducting and trapped ion approaches. Neutral atom quantum computers use individual neutral atoms rather than ions held in optical traps created by focused laser beams called optical tweezers. Arrays of hundreds of individually addressable neutral atoms have been demonstrated, and the qubit states are encoded in the hyperfine structure of the atomic ground state. Entangling operations between neutral atoms can be performed by exciting them to highly excited Rydberg states, where they interact strongly with neighboring atoms. This platform has attracted significant research and commercial interest because of its potential for large qubit arrays with connectivity. Topological qubits are a more speculative approach that would encode quantum information in the collective properties of a physical system rather than in any individual particle, making the qubit inherently protected from local errors by the topology of its quantum state. The theoretical foundation for topological qubits involves exotic quasi-particles called Majorana fermions, which exist at the boundaries of certain superconducting structures. Microsoft has been pursuing this approach. It would, if successful, dramatically reduce the overhead required for error correction, because the qubits would be intrinsically protected rather than requiring large numbers of physical qubits per logical qubit. The challenge is that the physical requirements for creating and manipulating topological qubits are demanding, and experimental progress has been slower than initially hoped. Quantum dots, silicon spin qubits, nitrogen vacancy centers in diamond, and other solid-state platforms are also under investigation. The diversity of approaches reflects the fact that the field has not yet identified a clear winning technology. Different platforms may prove optimal for different applications. Quantum communication may favor photonic approaches. Fault-tolerant quantum computation may favor superconducting or trapped ion systems. Certain specialized applications may favor entirely different platforms. The mapping of hardware to application is still being worked out. Beyond the hardware, the development of quantum algorithms is its own rich field. Since Shor's and Grover's algorithms in the 1990s, a significant catalog of quantum algorithms has been developed for problems ranging across number theory, simulation of physical systems, machine learning, linear algebra, optimization, and combination. The quantum singular value transformation, developed in recent years, provides a unified framework that encompasses many of these algorithms as special cases, allowing algorithm designers to construct new quantum speedups more systematically. Quantum machine learning algorithms exist that can, under certain conditions and with access to quantum random access memory, accelerate matrix operations central to machine learning. Though the conditions required for these speedups to manifest in practice are more restrictive than initial results suggested, the variational quantum eigens, developed in 2014, is a hybrid algorithm designed for near-term quantum hardware, meaning hardware that is too noisy for fully fault-tolerant operation. It uses a classical optimizer to adjust the parameters of a quantum circuit, seeking the configuration of the circuit that minimizes an energy function corresponding to a physical system. This approach trades the theoretical guarantees of fault-tolerant algorithms for the practical possibility of running useful computations on current hardware at the cost of finding only approximate solutions. The quantum approximate optimization algorithm is a related approach for combinatorial optimization problems. These near-term algorithms are important because they provide a potential path to practical quantum advantage before fault-tolerant hardware arrives, even if the advantage they offer is less dramatic. The quantum internet, a network connecting quantum computers and quantum communication devices over long distances using quantum entanglement, is another active development front. A quantum internet would enable new forms of distributed computing, allow quantum processors at different locations to work together as if they were a single system, and extend quantum cryptographic protocols like quantum key distribution to global scale. Building a quantum internet requires the development of quantum repeaters, devices that can extend the range of quantum entanglement without the coherence degradation that prevents simple fiber optic transmission of quantum states over long distances. Quantum memory, capable of storing quantum states for extended periods, is a key enabling technology. Several experimental quantum network links have been demonstrated over distances of tens to hundreds of kilometers, and the construction of larger-scale quantum networks is ongoing in multiple countries. China's investment in quantum networking infrastructure has been particularly notable. The country has deployed extensive quantum key distribution networks and has demonstrated satellite-based quantum communication. These are not commercially mature systems. They are research infrastructure, but they represent a substantial and deliberate national commitment to building quantum network capability at scale. Europe, the United States, Japan, and other countries have launched major quantum initiatives, committing funding on the order of billions of dollars to quantum research, education, and development. The race is not merely academic, it is strategic. Quantum computing is recognized as a potential source of decisive advantage in cryptography, pharmaceutical development, materials, science, and AI training. Countries that develop strong quantum computing capabilities early may have structural advantages in several economically and strategically important domains. This is not the first time a fundamental technology transition has carried geopolitical weight. The development of transistor technology integrated circuits, and the internet all had this character. Quantum computing fits into this historical pattern while also being distinctive. It is more directly dependent on fundamental physics research than most previous technology generations, and the path from research to deployment is longer and less certain. What this means in practice is that the quantum computing field spans an unusual range of timescales simultaneously. There are researchers working on problems that will not be experimentally testable for decades. There are engineers working on improvements to current hardware that might appear in commercial products within the next few years. There are algorithm designers working on problems relevant to current noisy hardware, and others working on algorithms that require fault-tolerant machines that do not yet exist. There are businesses trying to identify which near-term applications might provide enough value to justify the current high cost of quantum computing access. These communities are all talking to each other, but they are also, in a very real sense, working on different timelines. The communication between these timescales is important, because progress at the basic research level enables progress at the engineering level, which enables progress at the application level. A breakthrough in quantum error correction theory might, after years of experimental work, translate into a reduction in the number of physical qubits required per logical qubit, which might bring a fault-tolerant quantum computer within reach of a larger set of organizations, which might enable a new class of pharmaceutical simulations, which might produce a new class of drug candidates. The chain is long and the links are uncertain, but the chain is real and it is moving. There is another dimension of quantum computing that is less often discussed in popular accounts, but is central to understanding its long-term significance. The way it forces a rethinking of what information is. For most of the history of computing, information has been treated as something abstract, something that can be copied, transmitted, stored, and processed without any fundamental physical cost other than energy and time. Classical information is, in a deep sense, substrate independent. The same bit can be encoded in the magnetization of a hard drive particle, in the voltage level of a transistor, in the ink on a page. The physical medium does not change the information content. You can copy a classical bit perfectly and without limit. Quantum information is different. The not-cloning theorem, proved independently by William Wouters and Wojciech Surek, and by Dennis Deeks in 1982, states that it is physically impossible to create a perfect copy of an unknown quantum state. If someone gives you a qubit in an unknown quantum state and asks you to produce two identical copies, you cannot do it without measuring the qubit first, and measuring the qubit destroys the superposition. There is no way around this. It is a consequence of the linearity of quantum mechanics, not an engineering limitation. It is as fundamental as the impossibility of traveling faster than light. This has a profound implication. Quantum information is physical in a way that classical information is not. It cannot be freely copied. It cannot be read without disturbance. It is, in a sense, more tightly bound to the physical systems that carry it. This is exactly why quantum key distribution works. An eavesdropper cannot copy the quantum key without disturbing it. The not-cloning theorem is a security guarantee, written into the fabric of physics. It also has implications for quantum computing. Quantum error correction cannot work by simply copying qubits and checking copies against each other, as classical error correction can. It requires more subtle techniques that detect and correct errors without ever actually reading the quantum state, using ancilla qubits and entanglement to extract just enough information about errors, to fix them without collapsing the superposition being computed. The no-cloning theorem and its cousin, the no-deleting theorem, which states that it is equally impossible to erase an unknown quantum state without trace, reflect a deep principle. Quantum information is conserved. It cannot be created from nothing, and it cannot disappear into nothing. It is always somewhere in the system, distributed across entangled qubits in ways that may not be locally accessible, but are globally present. This connects to one of the most fascinating open problems in theoretical physics, the black hole information paradox. When matter falls into a black hole, and the black hole subsequently evaporates through Hawking radiation, what happens to the information encoded in the infalling matter? Stephen Hawking's original calculation of black hole radiation suggested that the radiation was perfectly thermal, meaning it carried no information about what fell in. If true, this would mean that quantum information can be destroyed, violating the conservation principle that quantum mechanics requires. But if quantum mechanics is fundamentally correct, the information must be preserved somehow. The resolution of this paradox is not yet known, but quantum information theory has provided conceptual tools for thinking about it. The work of Jacob Bekenstein and Hawking on black hole thermodynamics established that black holes have entropy proportional to their surface area, not their volume. This is deeply connected to the holographic principle, the idea that the information content of a volume of space is encoded on its boundary surface. The holographic principle, in turn, is the conceptual foundation for the gauge gravity duality that was simulated in the Sycamore wormhole experiment. Understanding black hole information is not a separate problem from understanding quantum gravity and the holographic principle. They are the same problem approached from different directions. Quantum computers, by simulating holographic dynamics, may help clarify what is actually happening to information in the vicinity of black holes. This is speculative, and the path from current hardware to meaningful black hole simulations is long. But the connection is genuine. The same mathematical framework that describes quantum computing is the framework in which the deepest questions about space-time and information are being asked. John Presk, a physicist at Caltech, who coined the term quantum supremacy, and has been one of the leading theorists of quantum computing for decades, has written and spoken extensively about the deep connection between quantum information science and fundamental physics. His view is that the study of quantum information is not merely a branch of computer science or engineering. It is a new lens through which to understand the structure of physical law, the insights that quantum computing requires, about how to maintain quantum coherence, how to correct errors in quantum systems, how to characterize quantum channels and their capacities, turn out to illuminate questions about how the universe processes information at every scale. This bidirectional relationship, where quantum computing informs physics and physics informs quantum computing, is one of the most intellectually exciting aspects of the field. It is rare for an engineering pursuit to be simultaneously one of the most advanced experiments in fundamental science, but quantum computing occupies exactly that position. Consider the challenge of characterizing a quantum processor. When you build a quantum computer with 100 qubits, you want to know how well it is working. But the quantum state of 100 qubits lives in a Hilbert space with 2 to the power of 100 dimensions. That is a number with 30 zeros, far more than could ever be written down, let alone measured. You cannot simply read out the full quantum state of the computer and check whether it matches what it should be. The measurement would collapse the state, and there would be far too many parameters to measure anyway. This is the problem of quantum tomography, and it requires sophisticated statistical techniques and careful experimental design. You run the same circuit many times, measure different observables each time, and use the statistics to reconstruct a characterization of the quantum state, not the full state, but enough information about it to verify that the computer is behaving as intended. As quantum computers grow in size, even this partial characterization becomes exponentially harder, and new tools are needed to verify quantum computation without full tomography. The problem of verifying that a quantum computer is actually doing what it claims to do, that it is genuinely quantum rather than a classical system mimicking quantum behavior, is a deep one. For small systems, classical simulation can verify quantum output, but as the system grows beyond the point where classical simulation is feasible, how do you know the quantum computer is correct? A set of techniques called quantum verification and certification are being developed to address this. Some involve cleverly designed tests that only a genuinely quantum system could pass with high probability. Others rely on cross-checking between multiple quantum processors. This is not merely a technical challenge. It is a philosophical one about what it means to trust a computation. One proposed approach involves having the quantum computer prove its work interactively, engaging in a protocol with a classical verifier who cannot themselves simulate the quantum computation, but can still become convinced that the result is correct with high probability. The existence of such protocols in principle is a significant theoretical result, though making them practical on real hardware remains a challenge. The quest for fault-tolerant quantum computing has also produced some of the most mathematically beautiful results in the field. The threshold theorem, proved in the late 1990s, established that if the error rate per operation in a quantum computer falls below a certain threshold, arbitrarily long quantum computations can be performed reliably by adding more qubits for error correction. The overhead in qubits and operations required for fault tolerance is polynomial in the size of the computation, not exponential. This was a crucial theoretical result because it proved that in principle, the noise of real hardware is not a fundamental barrier to quantum computation, only an engineering challenge. The proof of the threshold theorem drew on ideas from topology, information theory, and coding theory. The error correction codes used in quantum computing, the surface code, the color code, the toric code, are not arbitrary. They have specific geometric structures that allow errors to be identified and corrected efficiently. The surface code, for instance, arranges qubits on a two-dimensional lattice and uses measurements of stabilizer operators to identify errors without disturbing the logical information. The error correction process is, in a deep sense, a form of topological protection. Errors must form connected paths across the entire lattice to go undetected, and the probability of such large-scale errors is exponentially suppressed by the lattice size. This connection to topology is not a coincidence. Topology is the branch of mathematics concerned with properties that are preserved under continuous deformation. A coffee mug and a donut are topologically equivalent because one can be continuously deformed into the other. Topological properties are intrinsically robust. They cannot be changed by small local perturbations. Encoding quantum information in topological properties of a system is a way of making that information robust against local errors. The quest for topological qubits is at bottom. The quest to encode quantum information in the topology of a physical system, achieving error protection that is built into the hardware rather than layered on through software. The history of error correction in classical computing is instructive here. Early computers had no error correction. As computers became more reliable, error correction became less necessary for most operations. But error correction remains present in storage systems, communication links, and memory modules. As quantum hardware matures, the balance between hardware reliability and error correction overhead will shift. The most advanced quantum computers of the future will likely operate with intrinsically higher quality qubits, reducing the error correction overhead, which will make fault-tolerant computation more accessible and less resource-intensive. This maturation process is inevitable, but the timescale is uncertain. Progress in quantum hardware has consistently exceeded the expectations of pessimists and fallen short of the most optimistic forecasts. The realistic picture is one of continued steady progress with occasional dramatic leaps. Against a backdrop of genuinely hard engineering, challenges that may require unexpected theoretical insights to overcome, the question of what quantum computers will ultimately be good for, once the hardware matures, is one where the answers that seem most certain are probably the ones that will be most disrupted by surprises. In the 1950s, when classical computers were first being built, nobody anticipated that they would become the platform for social networks, financial trading algorithms, video games, or global logistics management. The full scope of what quantum computers will enable is similarly unpredictable. The applications most confidently predicted today, cryptography, quantum simulation, optimization, are probably correct as first approximations, but the applications that turn out to be most transformative may be ones that require ways of thinking about quantum algorithms and quantum information that are not yet fully developed. What seems clear is that we are in a period analogous to the early days of classical computing, where the hardware is fragile, expensive, difficult to program, limited in scale, and comprehensible only to specialists. The computers of this period did not look like the computers that changed the world. They were room-sized, prone to failure, accessible only to large institutions, and useful for only a narrow class of problems. But the fundamental logic was correct. The ideas were right. The engineering challenges were real but not impossible, and the trajectory from those early machines to the devices of today is one of the most dramatic in human history. Quantum computing is not guaranteed to follow the same trajectory. The challenges are different in kind, not just in degree, but the fundamental logic is also correct. The physics is real. The theoretical speed-ups are proven for at least some important problems. The hardware is improving, and the implications, if the hardware continues to improve, are as transformative as any technology development in human history. Every major advance in how humans process information has reorganized civilization. Writing reorganized memory and communication. Printing reorganized knowledge distribution. Classical computing reorganized calculation, information management, and communication again. The internet reorganized access to information and enabled new forms of economic and social organization. Each transition preserved much of what came before while adding a qualitatively new layer of capability. Quantum computing, when and if it matures to practical scale, will add a layer that is qualitatively different from everything that preceded it. Not because it is faster, not because it stores more, not because it communicates more efficiently, but because it introduces a kind of computation that was not previously possible. Computation that is genuinely quantum mechanical, that can directly simulate and reason about the quantum world, that can exploit entanglement as a resource, that can solve problems for which no classical solution exists. The coin flip that began this story, the 266 flips, the incomprehensible space of possibilities, was not just an illustration of complexity. It was an illustration of why classical tools are not sufficient. The universe contains complexity that classical logic cannot encompass. The universe's own processes operate by quantum rules, not by binary rules. Building machines that operate by those same quantum rules is the closest thing we have ever attempted to build in a tool that thinks in the language of nature itself. Whether that attempt succeeds fully, whether fault-tolerant quantum computers of practical scale are built in 15 years or 50 years, whether new algorithms emerge that we have not anticipated, whether the hardware challenges yield to engineering cleverness or require theoretical breakthroughs? These questions remain open. The answers will be written by thousands of physicists, engineers, mathematicians, and computer scientists, working across dozens of countries over the coming decades. What is not open is the significance of the question. The development of quantum computing is not a narrow engineering project or a niche academic pursuit. It is one of the defining scientific and technological endeavors of this century. It sits at the intersection of the most fundamental questions about the nature of reality and the most urgent, practical challenges of a civilization built on information. It asks what computation means when nature is the computer. And it is just getting started. There is a specific aspect of quantum computing that deserves more detailed examination, because it illustrates both the power of quantum mechanics and the depth of the engineering challenge in a particularly concrete way. That aspect is the quantum Fourier transform. The Fourier transform is one of the most important mathematical operations in science and engineering. It converts a function of time or space into a function of frequency, decomposing a complex signal into its constituent oscillating components. Every time your phone processes audio, analyzes images, compresses files, or performs signal processing of any kind, the classical fast Fourier transform is likely involved. It underlies MRI imaging, radar, telecommunications, spectroscopy, and an enormous range of other technologies. The classical fast Fourier transform is already an impressive algorithm. For a signal with n data points, it computes the Fourier transform using on the order of n times the logarithm of n operations. A vast improvement over the naive approach, which requires n-squared operations. This is one of the most important algorithmic improvements in the history of computation. The quantum Fourier transform accomplishes the same mathematical operation, using on the order of the logarithm of n times the logarithm of n operations, an exponential speed-up over even the classical fast Fourier transform. This is the core subroutine that Shor's algorithm uses to find the periodicity structure that reveals the factors of large numbers. The quantum Fourier transform is able to achieve this by using quantum parallelism to evaluate the transform across an exponential superposition of inputs simultaneously. But here is the subtle point that is often missed in popular accounts. The output of the quantum Fourier transform is a quantum state that encodes the Fourier coefficients in its amplitudes. You cannot simply read out all those coefficients by measuring, because measurement collapses the quantum state to a single outcome. What you can do is design quantum algorithms that use the quantum Fourier transform as a subroutine in a larger circuit that extracts specific useful information from it. Shor's algorithm is a masterpiece of this kind of design. It uses the quantum Fourier transform to find the period of a specific function, and from that period extracts the factors of the large number. This illustrates a general principle of quantum algorithm design. You do not get direct access to the exponentially large computational space the quantum computer explores. You get access to the result of a carefully orchestrated interference pattern across that space. The skill of quantum algorithm design lies in constructing circuits where the right answer emerges from this interference, and where the information you need can be extracted from the final measurement. This is why quantum algorithm design is so challenging, and why new quantum algorithms are not discovered easily. You cannot just write a program in the classical sense. You need to design an interference structure, a circuit whose global behavior across an exponential space of possibilities produces the answer you need in a form you can measure. The programming model for quantum computers is fundamentally different from classical programming, and developing the intuitions and tools for it is an ongoing research challenge. Programming environments for quantum computers have advanced considerably. The quantum programming languages, Qiskit, developed by IBM, Cirq from Google, Qubits, and others provide abstractions for specifying quantum circuits and running them on simulators or actual quantum hardware. These tools make quantum programming accessible to researchers who are not hardware physicists, but they are still operating at a relatively low level of abstraction. The equivalent of high-level programming languages and compilers for classical computing is still being developed for quantum systems. Quantum software encompasses not just programming languages, but the full stack of tools needed to translate a high-level algorithm description into the specific pulse sequences that drive the physical qubits of a quantum processor. This includes quantum compilers that optimize circuits for specific hardware architectures, error mitigation techniques that improve the reliability of near-term hardware without full fault tolerance, tools for characterizing and benchmarking quantum hardware, and simulation environments that allow algorithms to be tested classically before running on quantum hardware. This software stack is mature for classical computing, refined over decades by millions of contributors. For quantum computing, it is largely under active construction. The maturation of the quantum software stack is at least as important as the maturation of the hardware, and it is proceeding in parallel. One area where near-term quantum computers may provide genuine value without requiring full fault tolerance is in combination with classical optimization algorithms. Variational quantum algorithms, as mentioned earlier, use a classical optimizer to tune the parameters of a quantum circuit. The quantum circuit evaluates an objective function that would be classically expensive to evaluate, and the classical optimizer searches for the circuit parameters that minimize it. For problems in quantum chemistry and materials science, where the objective function is the energy of a quantum system, this hybrid approach may provide useful approximate results on hardware available within the next few years. The question is whether the quantum circuits required are shallow and noisy tolerant enough to work reliably on near-term hardware, and whether the problems they address are ones that classical methods cannot handle adequately. Research on this question is producing mixed results. For small quantum systems, classical methods can often match or exceed what near-term quantum hardware can do, because the quantum hardware introduces noise that classical simulation can avoid. But as system sizes grow beyond what classical simulation can handle, quantum hardware may find a niche even without full fault tolerance. This is the near-term quantum advantage question, and it is separate from the long-term fault-tolerant quantum advantage question. Both questions are active research areas. The answer to the near-term question will determine whether quantum computing provides practical value in the next decade. The answer to the long-term question will determine whether quantum computing transforms science and industry in the way its proponents envision. Beyond the purely computational applications, quantum technologies include quantum sensing and quantum metrology, which exploit quantum mechanical effects to make measurements with precision beyond what classical physics allows. Atomic clocks, the most precise timekeeping instruments ever built, already exploit quantum mechanical transitions in atoms to achieve stability that classical oscillators cannot match. Quantum gravimeters, quantum magnetometers, and quantum gyroscopes are being developed that can measure gravitational fields, magnetic fields, and rotation with precision that opens new applications in navigation, geological surveying, medical imaging, and fundamental physics. The development of quantum sensors does not require the same scale of quantum coherence as quantum computing, making it in some ways more tractable. Several quantum sensing applications are already commercially available or in advanced development. The network of quantum technologies encompassing quantum computing, quantum communication, and quantum sensing, forms a broader ecosystem than any single application. The components of this ecosystem will develop at different rates and find practical use at different times. Some quantum technologies are already in use. Others are a decade away. Others may be further still. Understanding this ecosystem of quantum technologies requires abandoning the popular mental model in which quantum computing is one thing, with one timeline and one set of applications. It is a family of technologies rooted in a common physical principle, but diversified across an enormous range of engineering approaches and application domains. The scientific foundation is unified. The engineering expressions of that foundation are multiple and varied. Looking at the trajectory over the last decade, the field of quantum computing has moved from a largely theoretical and experimental discipline to one with substantial commercial investment. Multiple competing hardware platforms, a growing software ecosystem, and early demonstrations of quantum advantage on carefully chosen problems. The next decade will likely see fault-tolerant quantum computing become experimentally demonstrated, though not necessarily practically scaled. The decade after that may see the first practical fault-tolerant applications in chemistry, materials, and cryptographic testing. The full realization of transformative quantum applications may be 30 to 50 years away, though history suggests both the timeline and the specific applications will surprise us. What is not in doubt is that the question of how to build machines that compute using quantum mechanical principles is one of the most important engineering questions of the current era. The physics says it is possible. The mathematics says it would be transformative for at least some important problems. The engineering is hard and the timeline is uncertain, but it is being worked on by some of the most talented scientists and engineers in the world, with resources and institutional support growing rapidly. The story of quantum computing is not a story that has reached its conclusion. It is a story in early chapters where the foundations have been laid. The first demonstrations of the central phenomena have been achieved, and the direction of travel is clear even if the destination is not yet in sight. Every generation of students entering physics and computer science programs today will, if they enter quantum information science, spend their careers on problems that are genuinely open. The field offers the rare combination of mathematical depth, experimental challenge, fundamental scientific importance, and potential technological impact that attracts the best minds across disciplines. The surprising fact that began this story, the impossibility of enumerating the sequences from 266 coin flips, was a gateway to something much larger. It pointed to the gap between what classical tools can handle and what the universe actually contains. Quantum computing is the first systematic attempt to close that gap, to build tools that can navigate the exponentially complex quantum landscape that underlies the apparently simpler world we observe at everyday scales. Whether those tools will ultimately let us unlock the structure of new materials, develop drugs that target diseases that currently defeat medicine, probe the dynamics of the early universe, understand what happens inside black holes, break and build the cryptographic systems that protect civilizations' information infrastructure, or do things we cannot currently imagine. They are being built now, in laboratories, in startups, in university research groups, in national research facilities, in the most advanced physics departments in the world. Slowly at first, then, if history is any guide, faster than anyone expects. The universe, at its most fundamental level, is a quantum mechanical system. The machines we are building to understand and emulate its computational nature are not merely tools. They are, in the deepest sense, mirrors, and what they will show us when they are mature enough to reflect clearly we do not yet know. The Schrödinger equation at the heart of quantum mechanics is not just a description of how small particles move. It is a description of how information evolves. When a wave function spreads across possibilities, when it interferes with itself, when it collapses upon measurement, all of these are information theoretic events as much as physical ones. The physicists who developed quantum mechanics in the 1920s were, without knowing it, laying the foundation for a new theory of information that the engineers of the 21st century are now trying to build into machines. The distance between Schrödinger writing down his equation in 1926 and Google's Willow processor solving benchmarks no classical computer could solve is almost exactly 1 century. In that century, the physical science became an engineering reality. Not fully, not without enormous remaining challenges, but real enough that the machines exist, that they run, that they solve problems, that they demonstrate phenomena no classical system can replicate. The next century will determine how far the engineering catches up with the physics, how many of the theoretical advantages become practical tools, how deeply quantum computing reshapes the scientific and technological landscape. The probability of significant surprises along the way, both obstacles and breakthroughs not currently anticipated, is high. The probability that the fundamental physics is wrong is essentially zero. Quantum mechanics is the most precisely tested theory in the history of science. The question is never whether quantum computers can work in principle. It is only how to make them work at scale. That is the challenge our generation is handing to the next. And it is, by any measure, a worthy one.